Okay, so in the previous video, we saw an example where we tried to fit a model of a given complexity with models of varying complexity. And here we saw that when we try and fit a model or fit a relationship between a target y and features x with a too simple model, we are subject to underfitting. The model doesn't really capture, the model is not capable of capturing the relationship between the target and the features. But we can also fit two complex models where we accidentally fit spurious relations in the model that are not in fact there. So that's overfitting. So how do we cure the curse of overfitting with regularization? That will be the topic of this video. So how might we solve the problem of overfitting? So considering what we just saw, we need to find a way to first reduce the number of variables considered in the model without really knowing which to remove. But then we also need to reduce the size of the estimated weights, but we don't know how much we need to reduce them by. So that's the fundamental questions here. So why do we regularize? So we do that to mitigate overfitting. That will generally give us better model predictions out of sample, but it will not, as we just saw before in the previous video, give us better will not give us better predictions in sample, but it's the out of sample predictions that we are interested in, and these are the predictions that we need to make with as high as accuracy as possible. And how do we then regularize? We do that by doing the two things that I just mentioned before. We make sure to fit models that are not too complex by both reduce the number of variables considered and reduce the size of the estimated weights. Okay, so what does regularization look like? So in regression models, when we regularize, we will generally add a penalty term to our optimization procedure in the following way. So instead of just minimizing the mean square error, so the expected squared distance between our true targets and our predictions with respect to our weights, our coefficients, we'll also add a penalty term that penalizes us for our choice of coefficients. So the intuition for this is that when we choose larger, doing this, when we choose larger model parameters, we will obtain a larger penalty to our measure of the quality of the model. So as we saw in the previous video, we had these exploding coefficients, but then if we penalize the size of the coefficients in our objective function, we will make our algorithm pick models with the smaller coefficient values. So therefore, or thereby the introduction of penalties implies that the increased model complexity has to be met with high increases in the precision of estimates. So that's basically similar to the intuition for the archaic information criterion and the Bayesian information criterion. So if you have at least when I followed the time series econometrics course during my bachelor studies in economics, these two information criterion were introduced. So the intuition for this is basically similar. So we only want to include higher betas when they also allow us to make more precise estimates. Okay, and what are some commonly used penalty functions? So there are two that you will generally see. So these are also called L1 and L2 regularization. So L1 regularization is also called lasso. So that's in this penalty expression here. So that's this one here. In lasso, that will be given by this expression here. So that's just the absolute value of each coefficient, right? So we're just summing the absolute value of the coefficients. So what can be shown in practice is that this makes our vector of estimated coefficients sparse, as it selects variables by removing some. So at least if lambda is high enough, it will simply, what we'll do in practice in many cases, it will simply just set sum of our coefficients to an exact 0. As we can see here, obviously this will only be the case if we also scale this penalty function appropriately, right? So if we choose a lambda close to 0, the penalties will not be important. While also if we have a very high lambda, we'll penalize our coefficients too much, and we might just risk ending up with only 0 coefficients. This is also something you will see later in this course. Okay, and the second type of regularization is called ridge regression. So in this case, our penalty is the squared value of each coefficient, and what can be shown is that that this reduces the coefficient size. So instead of just removing some coefficients, this will tend to reduce the coefficient size and basically attenuate. You can think of it, attenuate the coefficients towards 0. And this can be done relatively fast relative to L1 regularization, because there is actually an analytical solution to this problem. And one thing to note, and one thing that I'll also come back to, is that a elastic net, that's another type of penalization, is that simply uses a combination of both L1 regularization and L2 regularization. And this is quite popular in applied work. Okay, so in order to understand how lasso works, consider the following example here. So, or the following illustration. I don't think this is a perfect illustration, but I think it does provide intuition for how lasso works. So let these like circular objects be reflect our loss function, where the point here is the point that is the combination of weights that minimizes our loss function. And then let this diamond represent our penalization budget. So we can see that with lasso, our penalty is the sum of absolute values of our coefficients. So these combinations of weights will be associated with the same penalty. So now maybe just assume that we are accepting a given amount of penalization now. Given that amount of penalization, what parameters will we now choose? So given the amount of penalization that we will accept, the one that obtains the lowest loss, so that's the lowest value of this loss function represented with these circular objects, is the one where W1 has simply just been set to 0. So that's what I said. Lasso will tend to find will make our vector of coefficient sparse. It will set W1 to 0, and then we'll obtain some non-zero value for W2 in this case. Now consider the example of ridge regression. Here, because our penalty function is the sum of squared coefficients. Our penalties become this type of circular object. So again, assume that we are accepting the amount of penalization that's associated with this line here. What is it then? What combination of parameters is it then that minimizes our loss function? So that will be this combination here. So in this case, both of our coefficients are attenuated. None of them are set to 0, but both of them are attenuated towards 0. So that's to avoid this exploding coefficients issue, right? Okay, so finally, how might we describe the lambda of lasso and ridge? So we can really think of this. So stated differently, how do we pick a lambda? So how can we think about this lambda? So lambda is basically a hyperparameter that we can optimize over. And in the next module, I'll show you how we optimize over these lambdas. But we need to find the lambda that makes our out-of-sample predictions best, given our choice of penalties. So this is actually something that can be done, but this is what we call a hyperparameter. This is something that we want to optimize over. We may also ask, is there generalization of less on which? As I mentioned before, yes, there is. For instance, elastic net, which is basically just a combination of these two. So it allows both types of regularization, and it's fairly commonly applied. It is something that you will encounter a lot.